And we're live from downtown Mobay. Here we go. Yep, there is. If you do not have it, please come and get it from up here. It is on this table. It has a picture of a bow and arrow. It's right here. If you don't have one, come grab it. Okay. Ooh, I might have to break up that group right away. He's not even turned around facing the right way. You're good. Like, I might take them.
You know what? I'll take one for the team. And then I'll
I think that would be a good idea. Okay. Okay. Oh, what do we got there? But then there's also people behind me. Thank you.
I agree.
Thank you. We set this up last day. We have an arrow. There's 100 joules. This is potential energy, and it's going to be obviously released. And we're going to get the bow. The string is now loose because the arrow has disappeared. And probably bring that here as our arrow is flying along. And moving. It had here what kind of energy? Yeah, it's potential energy. What kind of energy does it have when it's flying through the air? This is kinetic energy. So that's a new type of energy. That's Ke, kinetic energy. Kinetic energy is energy of motion. And when I stood on top of the table yesterday, the worry was that I would convert all of my potential energy to energy of motion, at which point, when it hit the ground, it would then move that motion into my body, break all my legs, give me a concussion, and I'd have some time off. No, that'd be terrible. I'd probably have to answer emails while at a cast. Don't want to do that. How much kinetic energy will it have? By hands. Yes. It will not have 100. Yes.
Around this, like 90?
90, sure, that works. So let's say it has 90 joules of kinetic energy. One of the fundamental laws of the universe is that in any process, some of that energy is always wasted. There's 3 rules, and they can't win.
Where is it
You
wasted?
can't even break even, and it's not possible to stop playing the game. Yes?
Where is it wasted?
So where did the other energy go?
Yeah.
To the wood.
Mm-hmm.
Sound energy.
Sound. It goes whoosh as it goes by. So there is sound energy. Yeah, certainly the twang. In fact, if you think about it, you'll find another source of where that energy went. So it goes whoosh. What makes the sound of the twang? Pardon?
Elastic. I don't know.
Well, we had elastic potential energy, but then it went twang. You've answered one, so I'll go there. Air resistance. And so it has to push aside the air. So some of that kinetic energy is moving air particles. So it's losing some all the time. Any of you ever shot a bow? Go.
Yes.
Where does some of the energy go? Because it doesn't all go into the arrow. Where else does it go?
You.
The string wiggles and
Yeah.
the wood.
String wiggles. It goes twang because the whole thing vibrates. Anybody seen film or watched an arrow fly through the air? Yep. But what is the arrow doing? It is going forward. Some of that energy is not being used to drive the arrow forward. The arrow is doing other things often when it's flying through the air. It can be spinning, so we can have rotational motion. That is a form of kinetic energy, but it's a different kinetic energy than this one, than the speed. And the arrow will also wobble. The whole time it's flying in the air, it's going whoa, 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 because they're bendy. And so as it's going, that energy is dissipating the amount of energy. We're not going to worry about too much about things about friction, but we are going to worry about energy conversions. And we should be keeping in mind that when any energy converts, it goes into a variety of different forms. The energy is transformed into other things, and there's lots of things that it can transform into. When we talk about potential energy, the energy that converted to do work, that's what we're usually talking about when we mean work. We're talking about something useful we actually did. All the other stuff is just stuff that happens that we couldn't control. If we could make it so that the string didn't wobble enough as much, it would actually fly farther. If we could increase the amount at which we could pull that string, we could increase the elastic energy, and then we invent the crossbow, which has a different mechanism to put more energy into it. We are also going to focus on Earth's gravity. So if I give you a problem, you can always assume, unless I state otherwise, it's on planet Earth. And what is the number that relates to gravity on planet Earth? 9.80 meters per second squared. And what is that? No, it's not.
Mass.
It is not a mass. Mass is measured in kilograms.
It's a rate of acceleration.
It's a rate which is acceleration. Often students will guess like it's gravity, so it's a force. Gravity is not a force, it's an acceleration. You don't get the force until you apply some mass in there, and then you can feel the force. As I mentioned the other day, if you have, I don't know, a small insect drop out of the sky and hit you in the head, versus Mr. Neufeld falling out of a tree on top of you. One of those would probably be a little safer than the other. Although I will say for students who have walked under trees here that have those things that drop off, especially if you go to areas in the neighborhood where they have those really spiky ones, I forget what those are called, those chestnuts? I don't know. But they're really spiky, they can do a lot of damage when they hit you. Now the SI unit, now did I show you what a joule was last day? Like, did I demonstrate? One of the classes I didn't demonstrate.
Yeah, you need
At
demonstrate.
the very, very end. And that was a joule. Or a J. But fundamentally, it is a kilogram, meter times meter, so meter squared, per second squared. And at some point in physics, once you get used to these, you'll be able to recognize that as you start putting numbers together. And then at some point, you won't even need formulas, because you look at it and go, oh, I need energy, so I need a kilogram meter squared per second squared, and you just grab the data until you can multiply it together to get that. Makes things a little bit easier, but we'll start off with formulas. Anybody who still needs this from last day? Excellent. I am going to say that the next section did not work at all, and this is where I get to introduce you to magic. Magic exists because there's a car out there that I'm going to make it try and do something. And when I did it by myself this morning, it worked every time. And when I brought the class out there, it didn't work any of the time. And then when I made the class come back in, it then worked. So one of them was giving it the evil eye. And I'm waiting to find out who that is. But we'll see if it works today. We're going to talk about what the car is doing at different points, rather than me drawing it a whole bunch of times, which I'm going to do it on here to reference. But why don't we actually watch a car do that sort of thing? Please be quiet. It looks like there's people working on a test. I'm just going to want a little demo, it's a little loop-de-loop, just like that. Come on up.
I can watch a loop-de-loop.
Yeah, actually. Yeah, come back on. No, I'm coming. No, you got that stuff.
But for common talking, it behaves. So, view, zoom. Zoom.
What?
Excuse me?
Nothing.
Are these conversations you perhaps should not be having in class?
Yeah, I think so too.
So, there we go. No. No, that'll work. One. What is happening to velocity at 1?
Speed. Momentum.
Decrease.
You just said a random word. Momentum.
Decrease in kinetic energy.
It's decreasing.
It's KT is decreasing.
So we don't know what the acceleration is, but we do know something about the value of the acceleration. If the velocity is slowing down, what would the sign of the acceleration be? Negative. Because acceleration is a measure at how the velocity is changing. So although the velocity is positive, the acceleration is negative because the velocity is decreasing, and so a little bit of velocity is taken away. At green for this 2.
So acceleration is dependent on velocity.
Yes. I'm going to give you a question. The formula after. Velocity is at point 2. Increasing. Acceleration is positive. And then, last but not least, you're on a straight area, ignoring friction. What is your velocity?
Constant.
Nice one. We don't need clapping, unless you've had a hard day and you really need it.
I would appreciate some bonus.
Well then, ladies, gentlemen, honored guests, people of all ages, the correct answer. It does feel, have you ever walked out of a major test and you're like, there's no parade. There should be a parade because I just did something and nobody cares. It's like when you read a book and the most emotional, heart-wrenching thing ever just happened, and you look up, you may be in tears, and people are just going on about their daily lives. That's weird. What's the acceleration? For this, you should be able to get the exact value. Yeah. Acceleration is equal to 0. You calculate acceleration. Actually, does anybody already know the formula? It's done before in a different place. I don't. You don't do this in physics 9, do you? Pardon? There's no physics in grade 9? No. Okay. Acceleration. What was the factor that we were looking for? For, yes?
Delta speed, delta velocity over time.
Yeah, did you just look that up?
I remember.
No, you were vouching. No?
It's A equals to V minus U.
Yeah, so delta V over delta T. What does delta mean? Change. So that means change in. It's a capital delta from Greek? Latin? Greek, I think. No, Latin. Change in. So if you have, for example, delta x, that is equal to x final minus x initial. And we'll put F and I, but final minus initial. Always include that in there. It's a way of just shortening the formula since we all know what it means.
What does E represent again?
What is what?
Below V, it's an E. Is that an E?
That is a T.
That's
That is a lowercase t. There's a joke that goes with that, but yeah. I won't tell you. I will try not to script my t's. Delta V over delta t. We're looking for a change in velocity, and that has to happen over some amount of time. And so we need the amount of time that it has occurred in order to make a calculation. The full formula then would be acceleration is equal to V final minus V initial over time final minus time initial. We talked about velocity. What is velocity at delta of? Not kinetic energy. It would be measured in joules if it was. It does have to be over time. If you think about the units of measurement for give me a velocity as a unit of measurement. What do we measure it in? Kilometers per hour. That's a perfectly good one for velocity. Kilometers per hour. So you need, what is the one on top? What's kilometers? Distance. And over time. Acceleration is speed, which is measured, you could have kilometers per hour over hour. So that's how you get the squared. Meters per second squared. Meters per second per second. And that works out. And so if we wanted the formula for velocity, velocity equals the change in distance over the change in time. Once you know the units of one, you can work out all the other units. I was in an honors physics class, and the teacher said, I will give you a formula sheet. And we're like, oh, thank goodness. So many formulas. And then he said, but I'm not going to tell you what formulas I'm going to put on it. That is fairly useless because I don't know which formulas you're going to put on it. I am still going to study it all. And he goes, yeah, but I will provide formulas in there. That way you have a backup. So all he did is he walked in on the day of the test and he wrote and that is force is equal to mass times acceleration. That gives you the unit of Newton, and then he chuckled. If you know that, technically, yes, you can derive a heck of a lot of other formulas. I think it was just his way of playing a joke. I didn't like his sense of humor. But unlike some teachers, at least he had one. Oh, resistance to change in velocity. We haven't defined that. Why does this keep getting opened? What are you watching? You were in space! How would you measure your mass? You can't get on the weight scale anymore. It would show 0 because you'd both be floating there. It's hilarious watching astronauts when they return to Earth and they're doing an interview, and then they'll have their glass of water, and then they'll go like this, and then they'll just let go. And it'll smoke because they've forgotten that gravity will smash it on the ground. If you're in space, you need to know something's mass, which you often do for experiments. How do you measure the mass if you can't rely on gravity? Yeah.
Like, it's inertia?
Ooh, that's actually the word. But how would you then use its inertia to do it?
Maybe throw it at a wall at the same force as a different object and see the difference.
That's exactly what they do. They put it in a little container, and the little container just vibrates intensely, and the force at which it hits the side, they measure that. If it hits with more force, it has a higher mass. If it hits with less force, it has a lower mass, and they can use that to figure out how much it has. Because it's hard, the more and more mass something has, the harder and harder it is to push it, even in space. And so you can still use that. So inertia is a property of mass, and mass in physics is what we commonly refer to as weight. Weight is actually a force in newtons due to gravity, and that varies on all planets. But your mass doesn't change. You still have the same amount of matter. Just on planet Earth, they happen to be the same. An object in motion. Does anybody know an object in motion stays in motion unless acted on by an outside force. And this is why you can get up to tremendous speeds in Earth when we set up spaceships. We have the fastest, I think, thing we've ever built is like one of the Voyagers, because it just continuously accelerates. It's not accelerating very quickly, but it never stops, and there's no friction. So it just goes faster and faster and faster and faster and faster, and it's heading out of our solar. I think now has officially left our solar system and just is going to be going faster for quite a long time until it finally runs out of fuel or fuel near it in order to keep going.
How much fuel does it have?
Hmm?
How much fuel does it have?
A lot of the propulsion systems will use, like, you will pick up ions in space and use that for fuel, and you will have some sort of particle accelerator to run it through, or you put on a radioactive sample, use that for energy to develop a propulsion source. If it's just a rocket, then you have to take your fuel with you, and then you have a limited amount that you'll be able to use.
If there's no like resistance, will it just keep going?
Well, an object in motion stays in motion.
But if like even if it runs out of fuel.
Yeah, and when it runs out of fuel, it's just going to stop accelerating. The velocity will remain constant forever until it hits something. It's like they say, shoot for the moon, because even if you miss, you'll be amongst the stars, frozen, lifeless, and drifting forever until you're the farthest thing from everybody you love.
What if it just hits an uninhabited planet?
Oh, then it will stop.
Just like
It wouldn't actually matter if the planet was inhabited either, but I appreciated that you specified it was uninhabited, so it wouldn't hurt anybody.
it'd be like useless then, 'cause like the whole point of it was to like go to
Oh, if we're still getting measurements and it hits something that we didn't know was going to be there, that would be hugely useful. We actually had a problem with it. It started undergoing we couldn't read its signal anymore. Really weird stuff started happening, and it just turned out we had all sorts of theories. It turned out it was going through a section of the solar system that had a bit different kind of magnetic sphere than we thought it would. Another section went really weird. We got super excited because it meant possibly whole new laws of physics, and it just turned out the onboard computer was like malfunctioning. And once they calibrated it and fixed it, they were able to make it keep going. We'll quickly finish this off. We did this all down here. An object in, a change in velocity is officially acceleration. Units of acceleration are meters per second, or meters per second squared. When it climbed up, the velocity decreased, when it rides down, the velocity increases. And when it coasts, the velocity is constant. And the acceleration is 0. Now, while you're, my glasses are doing weird things. Oh, if you have not discovered Otter AI, it is fantastic.
What do we do?
Otter AI is a meeting AI. You put out a recorder, microphone or something, and it will just record everything that's everybody's saying if you're in a meeting, and then afterwards can generate you a task list, who to email, what was said, summaries. It's really, really, really good. So if you know that you have to go talk to someone, it's great. Or, I guess this just came to me now, let's say you're talking to people and you want to try and pick up and remember all the gossip. You could also do that.
Is that legal?
It's a bugging device.
I believe BC is a one-party recording state, but I would double check. It also depends whether or not the area you're in would count as an expectation of privacy. So if you carry it into a bathroom or your dorm room, probably not. But if you're in a hallway, maybe. We're also an independent school, which means we have private property, not public property. So it would count that.
So it's a bugging device.
No, it's literally for meetings. For people that want to remember to do things in meetings. It kind of takes the minutes, which is handy. Okay, quickly attends, Alexander, Aria, Ariel, Charlie's not here, Zhao, Guy, Isaac, Isabel, Jessica, Katie, Fiona is here, Natsuho, Stephen, Sterling, Jaden, Tyler. I think I've seen everybody else. 1, 2, 3. So, group maker. Tyler, you can join any group you wish.
Sweet.
I want you to first go and erase what's on the board, except don't erase this guy.
Oh.
And then,
What did we read?
I don't know. I think we're
Yeah, are you a brony, Tyler?
What does that mean?
oh,
A
the one
guy
we were doing
who likes My Little Pony?
crashed.
Yeah.
No, I'm not.
What? No, it's fun.
Okay, here's your problem. And ears up, because I'm going to evaluate. You can check with how other people are doing things, but when we evaluate physics problems, we are checking for, did you write the complete formula? Did you include your units with every single number? Do you have a final correctly calculated answer from those numbers? And does that have units? So if you show all of your work and it's wrong, you still get between proficient, high, or extending. But if you show only the correct answer with no units, that is emerging at best. Far more emphasis is placed on the process. So, using the formula for acceleration, Mr. Nouveau is traveling at 14 meters per second and saw the fuzz. The fuzz is the po-po. The police, the cops, the coppers. Okay. 2 seconds later, he was traveling at 56 meters. This is highly unrealistic. I am like going so fast. What was his acceleration? Also, I really did get a ticket the other day because I was going down to the store. I turned around and I was stopped, and the police officer said I was going 200 kilometers an hour. And I told him that was impossible because I'd only been driving for 5 minutes. It was 200 kilometers per hour. Physics jokes. Okay, right out, you firm with this? Once you're done, you can have a seat. And I'm going to go through and mark them.
So I think it's we do 56 minus 14.
Mhm.
You guys go. Oh, that's 44. It works twice. Over what's by that? Because it's over second square, right? So then 2 seconds later.
Where do you get that? Where do you get that?
I'm not saying that.
Where do you get that?
The instructions were write out the formula, make sure every number has units, make sure your final answer has units, and write the final answer.
Wait, what is 8? So.
What's the unit? Don't you have to write the unit?
Always, every number needs units. What do you hear about sig figs?
What's the unit of acceleration?
Okay.
What's the unit of acceleration?
Changing time? Yeah, changing time.
I do not know. Write it.
So it
Oh,
would
alright.
be 2.
Just write it at the same square.
Oh, it'd be. I thought it was square. It's oh, like the U meant faster. Yeah, the units are
What? 2.0.
And then, he was 2.0.
He was traveling at 14 meters per second and saw the fuzz. 2 seconds later, he was traveling at 56 meters per second. You sit down once you're done.
It's not square, but 14 minus.
The units for acceleration.
But no, it is. Boy doesn't play games. Actually, he was obviously tracking everyone else. 14 minus 1.
What?
You get no. You don't get minus 2. They need to kill each other. What was that? What was that? Wait, who's right? Who's right?
Both of us. Both of us are right.
Alright, I think it's 14. Huh? Did we do that right?
Tyler, what did you guys get?
41 units squared. No, that's not units, right? 41.
What is it to write out the formula? Do we need to like write equals delta V over delta T or just the number?
Did you say E?
Hey, sorry.
You know, it would, I find it sometimes helpful to write that. But if you've written the A and the delta and then the number.
Are you driving us?
Did you really just say he's driving?
No, that's because
We're minors.
Jaden, how you pressing keyboard?
Huh? Because I was
Okay.
at,
Oh.
no, because I was at Kinley.
Oh.
Dude, scissors, I was so proud of that. You're the type of guy to speed up when you see stuff on the seat.
I know you're a super seed there, bro.
Okay.
I didn't. You were really
On your attention.
No. Or sophomores.
I'll start, this was, that's the difference. So from here, we have the formula. We have no units. And no units. Then the units have appeared again. So I like to call these mystery numbers. Are they meters per second? Maybe they're widgets made in a factory per hour. We don't know. Other math, but we do get the correct answer, so the person can do math. I mean, obviously, we know what the numbers are, but the person reading it in whatever thing that you're trying to do may not. Also, 21 divided by 5? Well, this is correct, but this looks like someone's answer as well. Which answer is your answer? Is this something extra from something else? Okay. Be clear. It's helpful if you indicate. So, this is fine. This is entirely proficient. They missed out their units in one spot. Not bad. Go here. Got the formula. Excellent. Ooh. I mean, they didn't say what it was equal. You should do that. Otherwise, it's just a floating point of data, and we don't know what that's going to be. So keep that. But they did include it, so I really like that. And then again, no units, proficient. Oh, those are the wrong units. And so one of the useful things of keeping your units through is that'll correct you, because acceleration is not meters per second, that's velocity. What's acceleration? Meters per second squared, so that's below. Just look, and they have it all laid out. Oh dear. So, the top is the velocity. If this is commentary on how everybody else's work, you're missing the point of this. You're watching yours, you're picking up on other people's mistakes. Public, so you should be supportive. And not gossiping. Now you're talking.
Sorry, my fault, Mr. Nico.
The top of this is in meters. Is velocity measured in meters? No, probably copied down wrong. It's meters per second. So we've got to fix our units. They didn't keep their units all the way through. So once you fix that problem, this is not too bad. If you've missed out one unit, I don't know, it's probably maybe a proficient high. We have formula, full formula, not this problem, never mind. We have a V or sideways L and Batman glasses. I'm going to say that might be a V, but we need to say what it is, so final and initial would really help. The only reason you get away with doing a T is because the starting number is 0 seconds, and so it still technically should be T final minus T initial, but we tend to ignore it when we start at 0 seconds, that's okay. Meters per second is on the top, we have the units there, we got 42. 42 meters per second. That unit should be combined. So if you have meters per second, write meters per second squared. A bit messy, it depends on the mood I'm in, proficient, high, to extending, I am optimistic. All of the no's. This one, no units, proficient, correct answer, laid out the problem, really clear and easy to read, so I love that. And here we have up in the corner, all of the units. Do I see an equal sign over here?
Yes.
Oh, I think those are the weird commas. There we go. Equal sign, we've got the right answer, we've got the units below it, they should be up on the side, so let's just make it extending, not extending high. Because you're dividing by the units, it looks like. This one doesn't have units. Oh, formula, correct answer, units, no units in the middle, proficient or proficient high. So we need all of those pieces, and I'm being theatrical about going through and picking it all out because that will save your butt when the calculations get harder, particularly in Physics 11. So we have one more problem.
I leaned back in this bottle.
What? Sorry?
I leaned back in this bottle.
Oh. Just so that we've turned on the green button. So when the alarm goes in a few minutes, make sure you muster on the field in your house. Until that time,
What is it?
Okay.
What's your button?
You set up the fire.
Stop
clicking the green button, guys.
okay.
Bro, that was just my chair.
Click the fire alarm.
Ignore this question. So how I would look for to see the question. You've clearly got the formula. I do like seeing the expansion because if you get in that habit, I find students who like to jump ahead and quickly do things. Often there's a mistake there because you just fill in the wrong number. If you keep doing that consistently, I also like as a habit, write in the numbers of what they all are. It makes it very clear and easy to see. That's not mandatory. If you do this, this, and then that, that's fine. But there is a lot you can do just to make sure you don't make a mistake. If you want to be careful, put in all the units. 2 seconds minus 0 seconds, 21 meters per second. The actual problem that I would like you to do, because I did this one by accident and it turned out to be quite interesting. Mr. Neufeld was traveling at 27 kilometers an hour, 32 seconds after he left Brentwood. Actually says Brentwood, I'll fix that. And saw a small child. 97 seconds after he left Brentwood, he was traveling at 2 kilometers an hour. So apparently I slowed down, I didn't hit the child. What was his acceleration? There's a particular problem with this problem that turned into a good discussion. Let's go with this one. Ariel, you can join any group you want. Find your new partners.
No, it's not the same.
No, new partners. Find a spot on the board, erase the old stuff.
I think I know what the problem is. Converting kilometers per hour just I know this last year.
Oh, good. Well, that's only one possible solution. Yeah, I mean, you could convert it, and I showed people how to do that, which is the first discussion. But the second one is, no, that is a unit of acceleration. And we don't have gravity to worry about, so we're not minus anything else. What? It might be, would it be more meaningful to lose? One student has already seen this problem before, so they identified. Has anybody else identified what the problem is with all of these numbers? Keep going then.
Wait, is final?
Oh wait, it's 32 minus whatever that is. No, because look, after he left Brentwood 1.6, so you have to add.
Has anybody identified a problem with the numbers or the units? You have to convert what? Units. Now, we have hours and seconds. Those are different. You could keep the kilometers. I mean, it should be meters per second if you're using it with gravity and figuring out potential energy or kinetic energy or something. But given the only thing you're calculating is acceleration, you could do a calculation with kilometers per second squared. That's fine. If you're converting, this would be a useful exercise. You could convert the seconds into hours. Oh, no, you can't. You could. So let's say you have seconds. You know two relationships. What is it in terms of time? How many seconds and what? Fiona? What do you know about seconds in terms of its relation to other periods of time? 60 seconds equals 1 minute. Is there any relationship we know that would relate one of these with hours? 60 minutes equals 1 hour. These relationships, and just this particular way of doing things will be re-emphasized in Chem 11, Physics 11. This is incredibly useful. You can take any relationship and turn it into a fraction, and it's still true. So 60 seconds per minute and 1 minute per 60 seconds. It doesn't matter which one you use, you can choose. So if you have something like 32 seconds, which one of those has seconds in it? It's not a trick question. Which one of these has seconds in it? Louder. The top one. Do we want seconds? No. We want it to disappear. What does ABC divided by B equal? AC. So if we multiply this, gentlemen, those of you who are writing, I actually want you to stop. You want it to go away, so take the relationship that puts it on the bottom and put the minutes on top. Now you've gotten rid of it. You can cancel it like you can cancel in algebraic relationships. We want to now get rid of minutes, gets to hours. Which relationship are we going to use? 60 minutes equals 1 hour. Which one will go on top? Hour. Because that's the one we want in the end. We take it over 60 minutes. The minutes are separate from the number. They can be canceled separately. And so we canceled seconds, we canceled, you'll get a number of hours. Do that for this question. And now the question doesn't have a problem anymore. And the last point, stop. Now that you've had time to digest it, this is because the fact it was in seconds and hours was slightly offensive. You instinctively knew you had to make it the same. We are not using any constants. We're not using gravity. There's nothing else in meters per second squared. Why can't you just keep hours and seconds? If you want to do it and keep those numbers, I will say that you still can, and it won't be wrong. I'm just going to look at your final units really carefully. You can still do it. It'll be fine. Mm-hmm.